Hello, everybody, and welcome to our last session on part 3 of this course. Now, I had to restart my computer, and I'm always a little paranoid that things aren't set up. Can I just get confirmation from someone, voice or chat, that you can see and hear me? All right, perfect. All right, let's do it. Now, our last little topic is not a major one at this stage and is going to be fairly familiar, maybe completely. But it's going to be a bigger topic later. And I just want to sort of plant the seed, get things going so that when we start it properly or do it properly, then it's not completely from scratch. So we'll just do a basic introduction, overview of some area formulas of familiar polygons that we have talked about. It might not take us the whole session, doesn't matter. But it's an important session to just sort of get out of the way. It has to be put somewhere, so I put it here. All right, so let's start with our basic uh, shape. The most basic shape when it comes to area is the rectangle because it matches really it's used in the concept of area, that I have this basic unit square 1 by 1. It's my unit. And when I talk about area, the area of this rectangle, for example, I'm asking how many of these unit squares can fit in to this space. So of course, it's going to be the number of squares I can fit in, make a row, and then I'll stack the rows. So I'll have a number of squares that can fit here, depending on the, let's say, length of my rectangle, and the number of rows that will depend on the, let's say, the width of the rectangle. You can call it the height as well, doesn't matter. So let's call this L, and let's call this W. Why not? So if I know the length of this rectangle and the width, then by the basic concept of area, the area of this rectangle will be the number of unit squares that can fit, and that will be exactly the length times the width. Of course, at this stage in life, I hope everyone already knows that. But you introduce that, you sort of conclude that formula, lead students to that formula by way of this basic area concept of fitting a unit in and then counting the rows and columns, and that would be multiplication. Okay, so a rectangle. The simpler version or more restrictive version of the rectangle, if I can write properly here, is of course my square, just a special rectangle really, so the formula would not differ, but it is a simpler formula in that all the side lengths are the same. Then the area will be L times L or L squared, side length squared. Call it S side length, call it whatever you want. It's still the formula. But it's no different because a square is a, excuse me, I got all choked up about the square. It's so beautiful, so simple. It's just a simple rectangle, so the formula would, of course, fit with that more general formula. So let's make it a little bit more interesting at least. Keep my emotions in check. So what is next? Let's take the rectangle, there it is, and transform it by shifting the top edge a little bit sideways. I will then get a parallelogram. Parallelogram, like, I try my best to make it look parallel. I'll emphasize they are parallel just in case my drawing isn't perfect. I can see the rectangle as sort of a deformed parallelogram, if you will. Like pretend it's sort of a pliable material like rubber or something quite soft. I keep the bottom base fixed, but I sort of push the top to the right. I'll get this. Or what you could notice if I have a parallelogram, let's use some color. I have a triangle missing here, and that triangle is exactly the same as one I can cut out of the parallelogram. So if I cut out this right blue triangle and shift it over to the left, I've created this rectangle again. So if my rectangle had dimensions, let's say L, let's call it different. Let's make it a B for base, base B. Why not? Mix it up. And let's call this the height of the rectangle. Let's call it H. Then those lengths are still in the parallelogram. This bottom edge is the has length B, and I don't necessarily see the side length of any of this parallelogram as having H length, but if I draw a perpendicular line between the base and its corresponding parallel side, that will have length h, right? Because of the deformation or the correspondence to this rectangle. So that's why we don't call it a side length for the parallelogram. It's the height. It's the distance between the base and its corresponding opposite side, which is parallel. But because there's such a close link between these two that you can imagine going from the rectangle and deforming it to a parallelogram, you can think of the triangle cutting out and shifting it over, making the rectangle whichever way you want. The area of the parallelogram is the same as the area of the rectangle, which is the product of the two side lengths. Or in the case of just looking at the parallelogram, the length of the base times the height. Now I can pick any base and height, right? It doesn't really matter. I can have a more extreme example, like let's say it's a really angled one here. Maybe something like that. I'll emphasize that it is supposed to be parallel, the opposite sides. Then let's suppose this is my base here, whatever that length is. And now if I go up from that, I don't even get to that side. I have to extend it. That's out of place. I have to extend the parallel side further to see the perpendicular distance between the two parallel sides. Regardless, I would need to have that distance between the parallel sides. Now, of course, I could do the same thing and see this other pair of parallel sides as one of them being the base and then the perpendicular distance between them. It's not going to change anything. I sort of naturally just prefer to have the base as some horizontal bottom side, but it really doesn't matter, right? You could just rotate that and see this one as the base. Regardless, even though it looks a little strange perhaps, it doesn't have to be, the height doesn't have to be a line between or connecting the parallel sides. It's just the distance between the parallel lines that sit on those sides. Okay. So we have the formula for a parallelogram, which you may have seen before, you may remember, you may not. I don't know, but now we have it. Let's just zoom in on this page. And we'll just run through all the formulas and then do some examples at the end, where we want to look at just triangles and quadrilaterals for now. What if we had that triangle, given some side lengths, or that quadrilateral, or that one? Well, they're not always going to be as nice and structured as rectangles and parallelograms and squares. What else can we do? Well, we want to go to just covering the triangle before it is too late. Triangle. Now, I want to look at I could look at a rectangle, or I could look at a parallelogram. Let's look at a rectangle first, maybe. And we'll do a parallelogram as well. But that's not a parallelogram. The rectangle would be something I start with at elementary school to not have it be too general, but the parallelogram will be a little bit more general. So maybe a starting discussion, and then this will be more general. So any rectangle, or square even, I can split up. Let's just suppose here I have a base and I have a height, right? I can split that up into two triangles. Now, in the case of a rectangle, these triangles are going to be exactly the same. Whatever this area is, this is going to be the same area. Same area. So the area of one of these triangles, one triangle, is going to be 1/2 times the area of the rectangle, because they're the same. Now, before I do that, I suppose we look at similar and congruent shapes where if all the side lengths of the triangle match, like this, let's say this is number 1 and this is number 2, then I have this side length h, so that's the side length h. I have this side length b, that's the side length b, and I have the length that they share. All the sides are the same, then the two triangles have to be the same. In any case, so we get 1/2 times base times height. Dots, use time symbols, whatever, right? So the area of a triangle, 1/2 times base times height. Right here, 1/2 BH. But you could say, oh, isn't that just because of the rectangle? Well, no, in a parallelogram, which is sort of the rectangle is a special parallelogram, right? If I have a parallelogram, I could still do the same thing. I could do the long one here. I could do it this way. Doesn't really matter. Maybe mix it up a little. I still have the exact same triangle on either side. If I do it along this, it's not hard to be convinced, even for a new student, that this is the same triangle, copies of the same triangle. So even in this more general case, I have, let's go up here, maybe the height is the same. So I still have area 1 and area 2 for the triangle, but a single one of these triangles still has area 1/2 times the area of the parallelogram. Whoops. And that is 1/2 base times height again. So it doesn't matter how sort of skewed or obtuse or anything the triangle is. When I double up a nice right angle triangle with a 90-degree angle, sure, I get a rectangle. If I double up another triangle that's not a right angle triangle, I'll just get a parallelogram. But because those two areas are the same, it's always a half times base times height. Doesn't matter what the triangle may be. Okay, so I just want to cover the triangle. And while we're on the topic of a triangle, we have for a right angle triangle. Some people just say a right triangle. Ah, it never sounds good to me. Right angle triangle. I think it's just a habit based on how I learned it, right? Right angle triangle. Let's draw that. Let's do it like so. Now I do have a 90-degree angle here. My drawing isn't perfect. I indicate that's a 90-degree angle. Let's call this length A, this length B, and this length C. I think in terms of where this is in the book, I'm moving it up, but I think it's a nice place to have it here. For a right angle triangle, a very famous fella by the name of Pythagoras proved that there is a very strong relationship between the lengths of these sides, that the square of the perpendicular sides added together is always the square of the hypotenuse. And that really, if you look at the history and you think about it, really was a monumental uh, discovery that really changed the course of everything. It opened up uh, number theory, it opened up geometry, it opened up pretty much everything. All right. So I want to keep this in mind, not right away, but when we come to our examples. Might as well do it here. Then when it comes to a quadrilateral, there is one more general version I want to have a formula for. Space here, I hope I do. And that is the trapezoid. Trapezoid. Let's draw one. Oops, not a square. Remember the trapezoid has, I'll make it two parallel sides, right? They might not look parallel, but that is my intention. Doesn't have to be isosceles. These other two sides don't have to be the same length or anything. Trapezoid. Now, in deriving the formula or trying to figure out why the formula is what it is, instead of just memorizing it, understanding is always better. Yes, if I use something over and over and over, I do end up just doing it from memory, but I always have to have the ability to go back and explain why is this formula what it is? Well, let's see. In the case of the trapezoid, I'm going to have, let's say this bottom length is B for base. This top length, let's call that an A. Let me just put some brackets here. Maybe let me just emphasize in case there are more lines in a little while. That is B. That length is A. What I'm going to do very simply is cut this in half, maybe a little bit more perfectly than that. That's a little better. Okay, cut it in half. Any quadrilateral can be split up into two triangles. Now, these triangles are not the same because I work with a more general quadrilateral. But I can always do that by just connecting the opposite vertices. I've made two triangles. Let's call this triangle 1 and triangle 2. Now, let's write over here. The area of the trapezoid is equal to the area of the first triangle plus the area of the second triangle. Makes the shape, fills the shape. So if I look at, maybe the second one is a little nicer. Let's change the numbering. Let's make the bottom one number 1. Doesn't matter, right? I just like the base being bottom for my first triangle. It just feels a little bit nicer. Now for that, I know I need 1/2 base times height. What is the height? The height is going to be, not eraser mode, this distance between the two parallel lines again. I'm going to have that distance. So I'm going to need to know beforehand in order to calculate the area of the trapezoid, I need to know the distance, the perpendicular distance between the two parallel sides. Okay, now know that. Okay, that's fine. What about the area of the second triangle? Well, it's a little upside down. Its base is A, but its height from the base perpendicular up to the opposite vertex is still H. It has the same height. And together they make the area of the trapezoid. Now, I want to clean this up a little bit. I can take the half out as a common factor. I can take the H out as a common factor. And then I have B plus A. It really doesn't matter which way these things are shuffled, but I think it looks a little bit more familiar if I do it like this. Matter, right? I can swap inside the bracket. I can swap the multiplication. So the area of the trapezoid is sort of like a triangle. It has a look of a triangle formula, but of course it's not. It's a half times the sum of the lengths of the parallel sides times the height, which is the perpendicular distance between the parallel sides. Okay, so yes, can I make formulas for fancier shapes? Of course I can. But again, this is just our introduction. We don't need to have formulas for absolutely everything. Plus, at elementary school, we are not going to use fancier and fancier formulas. So what's the point? All right, so I think we've covered a good number here. We've covered rectangle, the square, the parallelogram, and its connection to the rectangle. We've covered the triangle and its formula, which is extremely important. Pythagoras is always there, just waiting to be used. Might be helpful. And the trapezoid is really as far as I want to go right now, using my knowledge of triangles, really. So let's have a look at a few examples, just a couple. One is I have a triangle where all the side lengths are given, for example, these side lengths. Now I know that, wait a minute. In order for me to find the formula for the area of a triangle, I need the height. Give me the height. I don't need all the side lengths. I really just need one side length and the height. So there are things that we can't necessarily do at this stage. We will, by the end of the course, handle it all, but people tend to think that, oh, I have these basic formulas, I should now be able to do absolutely everything. I am a little bit restricted by way of this height issue that I have to have sometimes. And sometimes it's not necessarily possible. I can't go and measure this perfectly anyway, right? It's just made up. So don't feel like, oh, now I have to be able to do everything for triangles and quadrilaterals. No, not necessarily. I do at this stage. We are going to expand on this, and I will be able to handle um, pretty much everything by the end. But at this stage, I kind of need the height. Kind of need the height. So this one, I can't go and measure it. I need the height, at least down to one line, and they're not giving me really any of it. And because this is a scalene triangle, I can't exploit the structure of it at all. If I could go and actually measure this and see, well, what is this length just stopping there? And what is that length? Well, then we have a chance. So let's just adapt this a little bit, realizing that we can't handle absolutely everything. We're not expected to measure it. If you just break it up for me and handle and present me with by not presenting me with the height, you need to give me a little more at least, right? Because I can't go and measure this perfectly. Now I've just made these up, so might not be the best. I think for the triangle to work, I'm gonna have to side lengths, or I might not actually get a triangle. Okay, so let's say here this length is maybe what, let's say a 2, and let's make that a 1. So now I know a little bit more. I do need to know this height in my formula, but they've given me enough to figure it out. They've given me enough now. Okay, so let's work with this one. But I wanted to show that I can't handle absolutely everything at this stage easily, but they'll give me enough to use the formulas that I do have. So let's split it up into two triangles, two right angle triangles. Even the triangle I can split up into smaller triangles. And the benefit of the right angle triangle is that I can get this h because there is a relationship between these three. So for triangle 1, I know that the sum of the squares of the perpendicular sides equals the square of the hypotenuse. From this, I can calculate the value of h. Now, just to make sure I do it in a way that makes everyone happy, there's certainly a short way to do this. Let's just calculate. This one I know is 4. 3.5 squared. Let's see it in the chat. Why not? 12.25. So then h squared is my 12.25 minus 4. So h squared is 8.25. So then h is going to be the square root of 8.25. That dot sits way too high. Let's see what that is. Happened. Of 8.25. I didn't have my equals. There we go. And what do we get here? Squeeze it in at the bottom. 2.87. If I want to round it, let's say round it to 3 decimal places. 2.8723. Now be aware that if my mouse cursor looks smaller. Let's press something by accident, whatever. If I have that as my final answer, great, no problem. Round it to whatever you want if the question doesn't specify. If the question specifies, round it to that. If I need to use this h in a future calculation, well, we should use the accurate number, or at least a good number of decimals. Otherwise, we're going to chip into this accuracy without realizing it. Okay, so let's go up here so I can see everything. So now I have enough information for both triangles. I know I didn't need it for, well, no, I did need it. I did need it for both. So area of one, triangle one, is now 1/2 times, I'm going to put a time symbol here, the base times the height. And when I do this calculation, I'll use the proper, most accurate version of h that I have. So let's do that. Well, it's actually not even necessary to do, right? When I look at this, the half and the 2 cancel, and I just get h. So that was nice. I'm always happy for little conveniences like that. So this is my final answer, and I will, well, it's not my final answer. So I'll round it in my presentation, but no, I can look it up exactly what it is. I don't want to write down too many decimals every time. So I have to be aware I present a rounded answer, but when I use it in the future, I'll use the most accurate version that I have. Area of 2, of triangle 2, I can see this 1 as the base, and then the height again is h. So now I have something to calculate, so let's see that using the most accurate version of h that I have. So it is 2.87226901 divided by 2. And we get 1.4361, I'll round it. So then the area of the triangle is, of course, the sum of the two areas. I'll write it out just because I don't know the comfort level that people have here. Maybe you have never done this, or it's been so long you don't even remember. So we'll just do it. Now I don't want to lose this fourth digit's accuracy. So when I do the calculation, I should just have at least 6 of the digits when I do addition, so I don't lose them. When I do multiplication and division, I could lose even more without realizing it. So I want to be as accurate as possible. Let's do it. 2.87228133. 1.436140066 would be enough. And I know to 4 decimal places, my area is 4.3084. Now, I admit this is not the only way to do it. But given the tools that we have, sticking to those formulas, the triangle formula needs the height. Needs the height. I could be given the height directly. Great, that'd be wonderful. Or I might have to use Pythagoras, but they'll give me enough to figure it out. Okay. But don't be afraid to break up my shapes into smaller shapes. I just want to see what the next one is. Okay, so here I have a trapezoid. Trapezoid. They don't give me this side length here. I don't know if they give me enough again. I need for the trapezoid formula to work directly, I need the length of the two parallel sides, and I need the distance between them. So again, they might give it to me directly, or they could tell me that this, not there. Let me just clarify this. The total length here is a 5, and this length over here is maybe 1.5. I need to find the height one way or another, either directly, they give it to me, or I need to have enough so that when I see part of it as a right angle triangle, I can find this height again. Great if they give it to me. Wonderful. But they might not. So let's maybe do it over here. To find the h first, which I need in my trapezoid formula, I know that the sum of the squares of the perpendicular sides in that triangle be the square of the hypotenuse. And then again, h squared is going to be, well, what is this? This is 9, 5 squared. Should I not know what that is? 225? Let's double check. Yep, 225 with a decimal, of course, 2.25. So I have 9 minus 2.25 there. That should be 6.75. So h is then the square root of 6.75, which is, let's see that, square root 6.75, 0.5981 if I round it, but I rounded it, I have to keep that in mind. Now, the area of the trapezoid is straightforward, 1/2 5 plus 3 times h. I don't write h. I know I have the value of h. I just write h. But when we do the calculation, we want to use the most accurate h that we have. Now, your calculator has a memory function. Probably you can store two numbers, depends on your calculator. So you don't have to type in all the decimals every time. Just use the memory function. Let's see here. So we have 1 divided by 2 times 8. 4, 5 plus 3 times h, which is 2.59807621135332. I type in all the decimals because I don't know if MathBot has a memory function. Maybe it does. I have not been bothered to figure it out. 3923, final answer. They don't give me units, so don't worry about the units. It's units squared. If this was centimeters, it would be square centimeters, of course, but we know the area units already. All right. So just want to be aware, I have my formulas. What do I need in my formula? They have to somehow give it to me or give me the opportunity to find it for these basic formulas. Let's do one more, and I think we've done everything we need to do. Let's look at this guy, which as much as I want to be able to handle everything, they really have to help me out here a little bit and give me some more information, at least to guide me in a direction, right? Because the only way I can do this is to go and measure extra information for myself. Now, there's multiple ways they could present it. I left it open so that I can discuss it. They can give it to me, give the information to me in a variety of ways. They might tell me if I split it up like that, they might give me this length and then maybe perpendicular distances from the triangle to that diagonal line, because I would need that, right? I would need more information. So they could give it to me via a diagonal line, and then the heights will be to that line. I have this top very obtuse triangle, and I have this bottom one. They could do that. Or they could tell me maybe this line is parallel to the bottom one. Now I can see, ooh, I can break it up as a triangle and a trapezoid. That'd be nice. That'd be nice. But I would have to have the height. So let's maybe make it as complicated as possible. Maybe they tell me, oh, that's a 90-degree angle. And even though this, let's see here, side, maybe they don't give it to me like that. Maybe they break it up into pieces. Let's say a 1 and a 3. And they tell me, let's just give me the height. Just give me the height. Simple. Let's say 1.5. Let's say 1.7. I'm totally guessing, right? My numbers might not all work out. It's just an example, right? But whatever numbers they give me, I'll just use that and not measure and overthink it. Regardless, I now have the idea of splitting this up into a triangle, top one here, and my trapezoid, number 2. So let's handle just a triangle. Triangle, which is number 1. Now for that, I don't need the hypotenuse in that triangle because if I look at which one do you want to see as the base? Maybe the top 3. The area is a half times the base of 3, and the height is this 1 because they are perpendicular already. One can be seen as the base, one can be seen as the height. So we're good to go there, 1.5. So that one's done. Nice, easy. But for the trapezoid, let's see what we need. And I'm just looking at examples and some variety to make you aware of things you have to be able to do, right? Trapezoid area, well, let's just set it up. I know it's a half times the sum of the parallel sides, which certainly is 6 plus, I don't know this side. Let's call it, what should we call it? L, length of that side. Don't know L, and I would need to. And then the 1.7, oopsie. The 1.7 will be the perpendicular distance, the height. Right, so I have everything except L, and I need L for my trapezoid formula. Way around it because the other two sides aren't parallel. I can't really exploit them with the information that's given. So I need to put a pin in that and just go on the side and figure out L. But the stop triangle can help me again because the sum of the squares of the perpendicular sides in that triangle, because it's a right angle triangle, has to be the square of the hypotenuse. So then L squared, this is 9, this is 1, so 10. And L is the square root of 10, which is not something I know off the top of my head. Square root of 10. I mean, maybe you knew. Of course it was 3.16, right? 2, 3 if I round it. But I will use it in the future, so I won't use a rounded number for that. So when we calculate the area of the trapezoid, I'll use that value of L. Let's do it. So a half times 6 plus 3.1622766016838. Ooh, that was lovely. Times 1.7. Random line. And I have 7.7879. Whatever the units squared. Area of my trapezoid. Now that's my line here was a little premature, wasn't it? Yeah, I got a little excited. Sorry. That's the trapezoid here, right? Number 2. The quadrilateral area of quadrilateral is area 1 plus area 2. I almost made that mistake. It's very easy to stop before you're actually done. Let's add those together. That shouldn't be too hard. 1.5 plus, I just need a few decimals here, 7.787936 would be fine. And we get 9.28 7, 9. That can get a line under it. Still a rounded answer, but some things to be aware of, right? I have to, in the larger uh, polygons that are a little bit more general, I have to come up with a plan for breaking it up into smaller pieces based on the information that they give me. I can't do absolutely everything, but they'll give me enough to break it up into something where I can use my earlier basic formulas. Right. So that gives us a fairly good introduction to area. We're going to revisit this a little bit later, make it a little bit fancier, but not too fancy. Not too fancy. That wraps up part 3. Wow, that's fast. Are there any questions? While you think of questions, I will get our schedule. Oh, I have the schedule right there. How can... All right. We are not in January. Get it out of here. We are in March. Now, we finished a little early. We finished today instead of the planned tomorrow. It's great. Great to be ahead of schedule. That just means tomorrow turns into a Q&A session. Now, don't go and complain to the college that I'm giving you too many Q&A sessions. That wasn't the plan. We're just so efficient. I did give you a little bit too many, but it's done. Can't undo it. We have 4 Q&A sessions before our quiz, in addition to a little Sunday morning if you want. You can use that time for an oral test. You can use that time for actual questions specific to the quiz. You can do whatever. The quiz is, of course, on part 3, which is... What is part 3? Geometry, polygons. Splitting constructions, we have a lot of them. It's nice. That's my favorite, especially with GeoGebra. Oh, it's so good. Then we did some unit conversions, length and area. We did some scaling. You made some transformations. So much fun. So lots of things to practice, more than necessarily calculate. You want to practice those construction steps. So just by practicing it, you'll memorize it. I'm glad. I never know how much extra time you need, right? But slowly as the semester goes, people might fall behind a little bit, so more time is good. You'll peek ahead in April as well. Look at all that time. Ooh, so many red blocks. Yeah, there's a lot of practice, especially in the constructions. Putting shapes inside a circle, putting circles inside a shape, circles outside a shape, transforming a shape. But it's fun, I think. I hope. Who knows? So use the time as you need to use the time. There's no obligation, there's no expectation. Whatever you need to do, right? So I may see you again before next Thursday. Not that I'm seeing you on Thursday, but still. Yeah, I haven't tried doing it on a touch screen. That might be tough. That might be tough. Yeah, I don't think I'll go that route. Also, be aware that after quiz 3, the schedule has changed. There are 2 yellow blocks, which means there will be videos in the playlist that for you to work through in your own time. That doesn't mean you can't ask questions later on, just sort of self-paced instead of live. As we start part 4, definitely ask if something's not clear, and then we will slowly wrap things up. Done. It's over so fast. Any thoughts in addition to what we have so far, or in response to what I said, or something? Again, let me know by email. Whatever you need, don't not ask your questions. especially as we get to the end. We want to wrap this up well. The geometry topic is a bit more varied, some calculations, some drawings, some stuff, uh, but it can be more fun as well. We want to end on a high note. Just checking to see if someone's typing. It looks like someone's typing. I can't wait to see the message that they're typing. Sometimes Discord says someone's typing and it never shows anything. Okay, good. Maybe I'll see you guys at some point. Otherwise, good luck on the quiz. And I guess we officially see each other again Tuesday the 23rd live. Wow. All right then. Until then.